Good morning, everyone. Have you guys received an email regarding the academic calendar?
Yes, sir.
So you can see, I think your mid-sem will start from 23rd September, right?
Yes, sir.
So this is within within 3 weeks now. You have less than 3 weeks time now. So you guys should prepare, and this in between you guys also have to move from your home to this campus. Have you guys received any email when you guys have to come?
September.
Yes, sir.
When it is this 12th September or 13th September?
13 September.
13, sir. 13.
Okay. So it's like you guys can start on 12th from your home and then you come here on 13th. I don't know whether there will be class on 12th or not. I'm not sure. So many of you guys will be traveling. Anyway, 12th is Thursday, so that is a tutorial day. Yeah. Let's see what happens. But important thing is that yeah, you have to prepare for the mid-sem. That is the important thing. Unit 1 we have almost covered. Okay, so you guys can start practicing on Unit 1. I'll give you some more assignment and tutorial. Mainly we have covered all the topics in the tutorial also. I'll give some additional system for practice on this Lagrangian setup and one more on the Hamiltonian setup. And I'll give some assignment so that you guys can calculate also. But otherwise, we have covered all the materials for Unit 1.
So,
Yes.
we have to fill an anti-ragging form for the college. So, in that, what should we fill as the director's name?
Director's name means I don't know. I haven't seen the form. What is
No,
meant?
actually, there's a column where I have to fill the name of the institute's director.
Okay, that is now is Professor Alok Kumar Singh. Now our director is Professor. Who wrote her? This is our director now, Professor Alok Kumar Singh. Okay.
Okay, sir.
So yeah, and you remember I'll take a quiz on this Monday on this up to Lagrangian's formalism. Okay. This will be how I'll give you 20 minutes to complete 3 or 4 problems, and you guys have to upload your answer sheet in the Google Classroom after you finish the quiz. Okay. Okay. Do you guys have any other question? Otherwise, I'll show you one more example of this Hamiltonian as you guys have asked, and then we'll move on to we'll start Unit 2. If you guys have any question. Okay, if you guys don't have question, then okay. What happened this one? Okay, then let me start. So in the last class, we discussed about how to set up the Hamiltonian. We have already discussed this. And basically the Hamilton's equation of motion, this you can write in this form. Okay, so today is 4th September. 4th September. So these are the Hamilton's equation of motion. Qj dot is equal to del H del Pj. Pj dot, this should be dot. Pj dot is equal to minus del H del Qj, and del H del T equal to minus del L del T. So these are the Hamilton's canonical equation of motion. These are called canonical because these variables are canonical. Like we told you that Pj is the conjugate momentum of the canonical momentum. So these variables are canonical to each other. Qj and Pj, they are canonical. Now I'll show one more example of this, how to set up this Hamiltonian. So we'll consider that particle moving under a central force. Okay, that we have also discussed how to set up the Hamiltonian Lagrangian. Particle moving under a central force. And the form of this force, we can consider, let's say, the force is given by minus k by r square. This is the form. Okay. Now, do you guys remember what will be the kinetic energy in this case? Let's say that this is moving on a plane. Okay, this is a two-dimensional problem. We have some mass m is attached to some string or something, let's say, and this is the mass m. This is the center, and this is the distance r between from origin to the mass, and this mass is moving under some force along this circular path, circular or elliptic path. So this is a typical central force problem. So now what will be the kinetic energy?
Half m r dot square plus r square theta dot square.
Half m r dot square plus. You guys should also do practice this how to write this in spherical polar coordinate. I told you guys that you guys should practice. And the potential energy will be minus k by r. This you can do by integrating f dot dr. F dot dr infinity to r. If you do this integration, then you can see this potential energy will be minus k by r. Then you can set up the Lagrangian. Then the Lagrangian will be L equal to T minus V. So this will be half m r dot square plus r square theta dot square plus k by r. And now if you remember the recipe that I told you, the general recipe to set up the Hamiltonian, that we have already completed this three steps. We know the generalized coordinate in this case. In this case, generalized coordinates are r and theta. And then we have set up the Lagrangian. Now we have to find out the generalized momentum. Now in this case, we have two generalized momentum because we have two generalized coordinates here. Here the generalized coordinates are r and theta. So we have two generalized momentum. So first momentum is, we can call PR, and PR will be del L del R dot. This is the generalized momentum PR, and this its value will be m R dot. This is PR, and we'll also have generalized momentum for theta, and that will be del L del theta dot, and this will be m r square theta dot. M r square theta dot. So we have completed this step number 3 now, that we know now the generalized momentum. Now we can set up the Hamiltonian H. Now H, I told you earlier that H either you can write as T plus V, or this is only when for some particular cases. Okay, like when this coordinate transformation, they do not involve time, or these are conservative system, that the potential does not depend on the differentiation of qj, that is qj dot. Then only you can write. Otherwise we have to use this form, that H equal to the summation of this. But you guys can confirm, like whatever you get, the Hamiltonian that you get from this result, whether they are equal to the T plus V or not. Like whatever we wrote for the simple pendulum, or in case of simple harmonic oscillator, you guys can confirm that the expression that you get using this expression, whether that is equal to T plus V or not. That you guys can confirm. Or in this case also you guys can confirm whether those are equivalent or not. So here H will be summation over Qj dot Pj minus L. So now here this is a summation over J. So we have two coordinates r and theta. So we have to write two coordinates. Sorry, this will not be summation. This will be r dot PR r dot pr plus theta dot p theta minus L. Okay, so r dot pr means this is basically m r dot square, theta dot p theta, that means m r square, theta dot square minus L. L is basically this expression again. This will be minus half m r dot square plus r square theta dot square minus k by r. If you simplify, this will be half m r dot square plus half m r square theta dot square minus k by r. Okay, so this is the step number 4, I think, right? This is the step number 4, that now we got this expression in terms of qj dot pj and t. We need to convert this qj dot to pj because we need the Hamiltonian in the form of qj, pj and t. That's called generalized coordinate, generalized momentum and time. But here we have r dot and theta dot. So we need to replace. So how can we replace? We replace by this, that from this expression you can say r dot is basically pr by m, and this expression you can say theta dot is basically p theta by m r square, and that you can put here half m pr by m square plus half m r square p theta by m r square minus k by r. Okay, so basically then what we'll get, p r square by 2m plus p theta square by twice m r square minus kr. Okay, so this is the form of the Hamiltonian. Okay, and this is a function of q, p and t, generalized coordinate, momentum and temperature. Now here you can see an important, you can make an important observation also from here. Can you guys see it? What is the important observation that you can make from here? If you look at the functional form, h is a function of what? H is a function of r. Let's start with momentum first. Let's start with r. H is a function of r, right? There is any theta dependence in this expression? There is no theta dependence, right? So h is not a function of theta. H is not a function of theta. It is a function of p and theta. So if this is not a function of this theta, then what we can say about this? Do you guys remember? We told you that if this Lagrangian or Hamiltonian, they do not involve a particular generalized coordinate, that has special name.
Cyclic.
Yes, so h is cyclic. Here theta is cyclic, and then we make one important observation, that when a particular coordinate is cyclic, you can make one more statement about that from there, that if theta is cyclic, then you can tell the corresponding conjugate momentum p theta is conserved or p theta is constant. That we have derived earlier, that if a particular generalized coordinate is cyclic, then you can say the corresponding conjugate momentum is conserved or constant. So here, if you look at the expression of the Hamiltonian, you can immediately tell that this Hamiltonian for this equation of motion, this p theta will be a constant of the motion. Okay, and this has many consequences also. Like these constant of motion, these are the constant of motion that we need to know. If you know the constant of motion, then you can describe the whole trajectory of the particle. Or when you learn quantum mechanics later, then you can tell that these constant of motion are basically associated with the quantum numbers in quantum mechanics. Okay, so whenever you see a cyclic coordinate, so basically our goal is to remove this dependence one by one, and then you can describe then you can solve the problem little by little as you remove one more constant from the system. So we can, from here we can set up the canonical equation of motion, and there also you will see that p theta will be a constant. Okay, but immediately from this expression also you can see that this is p theta is constant here. So now what is the equation of motion? We know that we know that qj dot q. So now here we have four equation of motion. So we know that qj dot this is equal to del h del pj. So now we have two here. J is basically r and theta. Okay, so we'll have two equation like this. Why this is not working? Okay, so qj dot first we can consider r dot equal to del h del pr. So what is del h del pr? That you can simply say this will be pr by m. This will be pr by m, right? Yes. Similarly, you will also get theta dot. This is r dot. You will get theta dot. This will be equals to del h del p theta, and del h del p theta is basically p theta by mr square, right? This will be p theta by mr square. P theta by mr square. And then you will also get pr dot. Pr dot, that will be equal to del h del r. What is del h by del r? Or not, this will be minus del h by del r, right? So what is del h by del r? P theta, there is p theta square. So this will be p theta square by twice m r cube. This minus will cancel, p theta square by twice m r cube, and this will be minus k by r square. This is pr dot. You will also get p theta dot, and p theta dot, this will be minus del h del theta, and this is 0. There is no theta dependence. So p theta dot is 0. That means p theta is constant. That we already I already told you that from this cyclic coordinate you can already tell that p theta is constant in this case. Okay. Now this is one equation, this is second equation, and this is the third equation, and this is of course the fourth equation that you can do from this Hamiltonian. And now you can further simplify. We have r dot equal to pr by m. We have r dot, this is equal to pr by m. So further you can tell r double dot, this will be equal to pr dot by m, and pr dot is basically this expression p theta square by twice m r cube, right? So this is basically pr dot by m, that you can say r double, this is r double dot pr by m, right? So this will be p theta square by twice m r cube minus k by m r square, r double dot, and p theta is constant. Let's say p theta is constant equal to some constant beta, let's say. Then you can say r double dot minus beta by twice m r cube plus k by m r square. This should be equal to 0. Okay, and this is the equation of motion for the central force problem. Okay, we should not have m here. We made some mistake somewhere. Can you guys see what is the mistake? We should not have m here. We have m here in this case. Do you guys see it where we have made mistake? Look, you guys check. We should not have m here. We should not have m in both the expression. In either of them, we should have m, not in both. You guys check, then confirm. Okay. Most likely we should not have m here. This m should not be there. You guys, but this will be the general form of the expression. Okay, for the central force problem. Okay, but any questions so far on this? Okay, but this one check. We made some mistake somewhere. This same should not be there. Okay, last thing I want to discuss that why we're taking this trouble of formulating this Lagrangian and the Hamiltonian mechanics. Okay, what is the advantage of over Newtonian mechanics that we are taking so much trouble. Okay, so we can so first thing is that you can see here whatever the problem we have solved so far. In this case, we mainly focused on the energy, and for force is already we have taken care of because we mostly dealt with generalized coordinate, and I told you that these generalized coordinates are independent of time. These generalized coordinates are independent of each other. That means that these constant forces that those are already taken care of when we are considering this formulation of Lagrangian or Lagrangian in terms of this generalized coordinate. So that is one big advantage, that you don't exactly need to know the nature of the form of the force that you are dealing with. Okay, so instead of force, you can focus on the work and energy. Okay, in case of Lagrangian formulation. So that is one. In many times you will see that you don't know that constant forces. In many cases, in case of, for example, in case of simple pendulum problem, we have not considered the constant forces. We know the constant forces is basically the force that the string that is attached to the mass, the bob with the rigid support, that provides the tension between this rigid support and the bob, and that counters the gravity, and that is the constant force there. But while deriving the Lagrangian equation of motion, we don't need to consider that force. We can simply, if we simply know the generalized coordinate, we can get to the equation of motion. And same thing also there in other problems as well. Like this Atwood meshing problem also you can see. We don't need to know the exact constant forces. Once if we can identify the generalized coordinate. So that is one big advantage. And second big advantage is that this symmetry. So we have not discussed much about symmetry. So symmetry plays a big role in physics. Okay, like if this from just by arguing based on the symmetry of the problem, you can know much more about a system. Okay, so in Lagrange's equation of motion, the symmetry operation, they are very important. Like if this part one particular symmetry, for let's say one symmetry is that if you move a system, if you translate a system from one point to another point, okay, this you can make a linear translation, that this point is system is here at this point, and you move the system somewhere here, making some linear translation. Okay, so those symmetry that is attached to some conservation law, we have discussed some of them, like this conservation of linear momentum, angular momentum, and those are basically related to the symmetry operation in the Lagrangian. So those are also inbuilt in Lagrangian. But the thing that you can more easily will understand is that this Newtonian mechanics, they will not work when you will study relativity or quantum mechanics. You will see that Newtonian mechanics is an approximation. It does not work well. But this formulation, this Lagrangian and the Hamiltonian formulation, particularly we'll see this Lagrangian formulation, it will be a good formalism in case of relativity. You will see there will be Lorentz transformation and that Lorentz invariance. Lagrangian will be Lorentz invariance there. Similarly, already you are studying, I think, quantum mechanics in your chemistry courses, and there you can see this. You have already studied Hamiltonian. So the concept is same, that based on this Hamiltonian, you can describe the quantum mechanics as well. So you can infer this same same concept of this Hamiltonian in the quantum mechanics as well. And there you can quantize um, various systems. Okay, these are few advantages of using Lagrangian. And another advantage is that so far we have only described this discrete degrees of freedom. That these degrees of freedom, we told you that these are either 1, 2, 3, 4, n 3n number of degrees of freedom. But in case of you will learn in unit 3 that there will be fields, there will be electromagnetic fields, and those, in case of electromagnetic fields, they are your degrees of freedom will be continuous degrees of freedom. And there also you can see this Lagrangian formulation that will work. You can write Lagrangian for a electromagnetic system there. I'll give you one problem in the tutorial also for electrical circuit, so that where you have to write the Lagrangian. But in case when we learn electromagnetism, there you can see that this you can write the Maxwell's equation. You are familiar with Maxwell's equation for electric and magnetic field. Those also you can write in terms of Lagrangian. Okay. So and these are few advantages of Lagrangian. Now also you can ask why. Okay, so after Lagrangian, why you have moved to Hamiltonian? What is the other benefit of using Hamiltonian? That is also you can ask. So you can see in one big advantage is that this Lagrange's equation of motion, those are, you can see the second order partial differential equation. This Lagrange's equation of motion. This you can see this Lagrange's equation of motion is del L del Qj dot minus del L del Qj equal to 0. So this is a second order differential equation. Okay. But Hamilton's equation of motion, that you can see that Qj dot, this is equal to del H del Pj. So this is a first order differential equation. So these are much easier to solve. Okay. So you need to do only one time. So that is one advantage. And second advantage is that here we have not discussed much about this. I told you that this Lagrangian, it depends on Qj dot and time. But I specifically told you that when you set up the Hamiltonian, you describe this in terms of Qj, Pj, and T. So here you can see in case of Lagrangian, we are talking about velocity. But here in case of Hamiltonian, we are talking about momentum. And this momentum is not the usual momentum that you knew so far. This momentum is generalized momentum. And here this position, this generalized coordinate and generalized momentum, those have independent status. In quantum mechanics, you have already seen that the uncertainty principle, that if you know the position very well, then you cannot know the momentum at the same time very precisely. There you have uncertainty relation. That position and momentum, energy and time, those are those dual variables. You will have some uncertainty relation. So there are many dual variables in physics. So these are conjugate variables. Okay. And here position and momentum, they have independent status. But here in case of Lagrangian formulation, this velocity is simply the derivative of the generalized coordinate. Okay, so these are not independent. So if you want to solve a Lagrangian problem, you just need to know the initial values of the position, and that's all. But then you also need to know the final values if you want to solve the Lagrangian. But in case of Hamiltonian, if you know the initial value of this generalized coordinate, generalized momentum, then you can describe the system. Okay, so some of this point you should note. Okay, maybe we can ask you in the exam that what are the advantages of using Lagrangian and Hamiltonian instead of Newtonian mechanics. Okay. And another advantage is that Hamiltonian, this you can easily quantize. When you learn quantum mechanics, there you will see that we are describing the system in terms of Hamiltonian. Okay. And those are easy to those you can easily quantize. So why we use UJ and PJ? So that is also important for statistical mechanics. Okay. So like we generally call this Q and P. This is called phase space. Okay. You will learn in statistical mechanics if you read sometimes later. That position and momentum they form a phase space. Okay. And this phase space describe the system. And this will see if you learn statistical mechanics, there you will have wide application of this position and momentum. We'll do a little bit of statistical mechanics, but not in depth. On this phase space and other problem. Phase space is this describes the trajectory of the particle. Like if a particle is moving, let's say along a straight line, then in this phase space how it looks like. So in this phase space we can describe the trajectory, and this Hamiltonian that will basically generate the trajectory, because if you see the Hamilton's equation of motion, that is basically related qj dot, this is basically del h del pj. This Hamiltonian basically generates the trajectory in this phase space. I know this many of this we have not learned it yet, but some of the general advantages, you read some books, you will get some idea what are the advantages, and note down some of the points that what are the advantages of Lagrangian and Hamiltonian. Okay, so few basic advantages that I told you, that in case of Lagrangian that you have already taken care of the forces. Okay, so that is one big advantages. Second thing is that the symmetry operation, that there those directly leads to conservation laws in case of Lagrangian. Okay, and that it works with relativity with relativistic mechanics, like this Lagrangian formulation. And in case of Hamiltonian, that this QJ and PJ, these are independent, and you can do quantum mechanics by using this concept of Hamiltonian. And also this has first order differential equation instead of second order differential equation. Okay, so these kind of advantages, and there are some disadvantages, not disadvantages, but little bit difficulty of using this Lagrangian and Hamiltonian also. For example, if you can see this setting up this Lagrangian and Hamiltonian, those are not very easy. Sometimes those can be little bit complicated, and if you particularly if you have frictional forces, we have not discussed the frictional forces. We mostly restricted ourselves to this conservative forces. But if you have frictional forces, then there will see it will be much more difficult to solve this problem using Lagrangian and Hamiltonian. Okay, list of chapters from Goldstein book. Goldstein book, which I think chapter 1 to let me see quickly. So in the Goldstein book, you need to read. If you guys follow my notes, that should be okay in most cases. So you need to read chapter 1, chapter 2, and chapter 8, 1, 2, and 8 in the Goldstein book. Chapter 1, 2, and 8. These three chapters in the Goldstein book.
सर मिड सेम में कहाँ तक आ रहा है ये हैमिल्टन तक?
No, mid-sem will be up to unit 2. That will start today. Unit 1 and unit 2.
यूनिट 2 नेम सर?
Unit 2 will start today. Unit 2 is one thermal physics will start. Okay, any other question? Any doubt? Otherwise, I'll start unit 2. In unit 2 today, okay, so in unit 2, basically, today I'll give you some we'll revise some of the concept of this probability and statistics, and then we'll actually start the unit 2 on next day, on Friday. Okay. I told you mid-sem syllabus it will be up to unit 1 and unit 2. Mid-sem, all of you have the syllabus, right? Mid-sem will be up to unit 1 and 2. Any other doubt up to for this Lagrangian and Hamiltonian? Okay, so okay, let's move on then. So far we have discussed mainly on this classical mechanics, this Newton's law, and this Newton's law, and this vector analysis. Yes, vector analysis will be there. Vector analysis is part of unit 1. It will be there. So next thing we want to discuss is about thermal physics and little bit of statistical mechanics also. So in thermal physics, we'll mostly restricted to classical regime, but we'll also discuss some of the quantum distributions like Fermi-Dirac and Bose-Einstein distribution function. But before going there, I want to revise little bit on the probability. I know you guys have already read in your class 12, but this is just for a revision, because you need to have idea about this distribution function, what it means actually, and how you can analyze this distribution function. Okay. So let's see. We'll start with probability. Can you guys tell me what you have learned on probability in class 12? Quickly, anyone? And why we need probability also? Anyone, what you have learned in class 12 on probability?
Sir, some theorems like Bayes theorems.
Have you learned about this on probability and both on probability and statistics about standard deviation, distribution function?
Yes, sir.
Okay. So we want, firstly, let's start with that why we want to know, we want to have probability on the first place. So for example, that we know that that whenever we start with a probability class, people tell you that like this example of a coin toss, that if you toss a coin, there will be 50% chance of a head and 50% chance of a tail, that you will get a tail. But why is it so? Why we are living into probability? Don't you know the all the can for example, if I give you all the forces, can you exactly determine whether it will be head or tail? Like let's say I toss a coin and then you know all the forces. There is nothing hidden, anything there. Then why we need to go to probability? As soon as you toss the coin, then at that point you know all the forces and how it is speeding, how far it will go. If you know the initial velocities and all this thing, then how far it will go, and then you can calculate when it will fall and which direction it will fall. Will you not be able to calculate?
So because you cannot predict the future.
There's nothing prediction. If I give you all the forces, then what is the problem?
So if we have all the forces, then we can essentially predict the future.
Yes, then why we need to put leaving it to probability that you will have some chances of head and some chances of tail. Any other answer? In this point toss problem, don't you know all the forces? Or any other similar system, like people also say throwing a dice. Hey, don't make unnecessary comments on the chat. Otherwise, I will disable this chat. Okay. If you have relevant question, then only you ask on the chat. Otherwise, I'll disable this chat. So one answer is that many of the times we don't know, or it is too difficult to know all the forces that is acting on that particle. Like if there is a small change on, let's say, wind velocity, that will also affect, or the direction. Okay. Or how exactly you have flipped, how exactly you have flipped the coins. Okay. So one answer is that those forces for this that physical event, all the forces we don't know precisely, or even if we know the precisely, solving those problems is very difficult. So compared to solving those difficult problems, if we just resort to probability, we'll get answer much easily. That is one of the answer. But the second answer is that when you learn in quantum mechanics, then you will see that our physical universe, those are both mostly quantum in nature, and there the standard is the probability. We don't know anything. We only know the probability of certain events or certain thing. That the events are not deterministic. That you can tell with 100% guarantee that this is going to happen. And and that is easy, that you can see easily in case of quantum particle, like if you have electrons, photons, phonons, those cases. But those are also equally applicable for macroscopic world. But in case of macroscopic world, those does not affect that much. For example, when you will see in quantum mechanics, now you have know that there will be electron but in quantum mechanics you will see that you cannot define the position of the electrons with a very precisely. You can only tell that okay, there will be some probability, let's say 50% probability that the electron will be there. So that will be inherently probabilistic in that case. Okay. So it is not always like that, not always that the problem is too difficult to solve, but the nature of the event is itself it's quantum probabilistic in many
पर
cases.
हाइजेनबर्ग अनसर्टेनिटी से नहीं होगा क्या?
Heisenberg uncertainty principle, that that there we have discussed probability or not in case of Heisenberg uncertainty principle. That is a different thing. I am telling you that events itself are probabilistic. That is not deterministic. Like if, for example, I am sitting here in classical mechanics, you can tell with guarantee that with 100% guarantee that you are sitting here there. But in quantum mechanics, you will not be 100% sure that I am sitting there. You can only tell that okay, there will be 99.999% probability that I am sitting here, but there will be certain 0.001% chance that I am not sitting there. So the physical world itself is probabilistic. Hey, who is making these comments on the chat? I'll remove. Who is this one? Sidhu Musewala. Don't rename you like this. I'll completely ban you from this class. Don't make unnecessary comments like this. Now, okay, so let's say this probability, in probability, that probability of happening events that is either zero, that generally falls between 0 and 1, right? That let's say if you do a coin toss, that getting a head or tail, that will be either 0 or 1. So this probability will be always between 0 and 1, right? This probability of a particular event. And if you sum over all the probabilities, that will be equal to 1. That these things you guys know. That if you sum over all the probabilities, for example, if you toss a coin 50 times, and then if you sum over probability of all the heads and all the tails, you will get 1. Okay, there will be 50% chance for heads and 50% chance of tail. Okay. Now, how do we from here, how we get the mean value of a quantity? Mean value of a quantity x. If you know the probability, if you know that the probability pi, then how can we calculate the mean value x? How can we get the mean value? Let's say you have done this coin toss for 100 times. Then what will be the mean value? How do we define the mean value in case of probability or the statistics?
It is the average value.
Yes, this is the average value. This is mean value x. How do we define the mean value?
Sigma xi pi by sigma x.
Mean value will be simply xi over pi. Xi means okay, let's say you are throwing a dice. So okay, you are throwing a dice. Okay, so whether you are getting 1, 2, 3, 4, 5, 6, or how much probability all these events have? All of them have probability 1/6, right? So for all these events to happen, the probability is pi is equal to 6, 1/6. So what is the mean value of x then will be? Then you can say mean value is basically 1 into 1/6 plus 2 into 1/6 plus 3 into 1/6 and so on up to 6 into 1/6. That will be the mean value if you throw the dice for let's say 100 or 1,000 times. If you do it 1,000 times, that will be the mean value of the dice that will get from throwing from this event, right? This will be the mean value, and what will be the mean squared value? Mean squared value will be mean squared means what will be x square. So that will be simply xi square pi. That will be the mean square value. Okay. This you can calculate for this throwing a dice, these events, that the outcomes are 1, 2, 3, 4, 5, and 6, and each have probability 1/6. Then what will be the mean value of x square? Now these are called discrete probability, because here that values that it will take one, let's say 1, 2, 3, 4, 5, 6. This we have only 6 values. Okay, and this is discrete. These are not continuous. It's not like the dice can take any value between 1 and 2. It can take only values 1, 2, 3, 4, 5, and 6. Okay. So in case of continuous probability, that the event can take any values between some specified range. That is called continuous probability. That is called continuous probability. So for example, let's say you fill up this cubic box with some gas. Okay, with a gas molecule. You keep one gas molecule in this cube. Okay, and then I ask you, what is the, let's say this is x, this is y, this is z coordinate. What is the what will be the z coordinate of the molecule? So z coordinate, let's say this is cube of dimension a. Okay, then what will be the value of the z coordinate?
Something in between 0 to A.
Something in between 0 to a. Between 0 to a. We don't know the exact value, but it will be between 0 to a. So this is the example of a continuous probability that it can take any value between 0 to a. Okay. And in such cases, we what we do, we generally take a strip between, let's say, z and dz, z and z plus dz. We take a small strip between this length z and z plus dz, and then we define the then we define the probability. And in such cases, the probability between z and, if you do it for the whole range, then this probability this will be equal to 1. Like in earlier cases, this total probability was 1. In this case also, the total probability of finding this particle between z and dz, if you count all the probability values, it will also be 1. And how we will define the mean value in this case? This will be x. Let's say we are defining some value in case of x, and this will be p of x dx. Similarly, x square, this will be x square px dx. And how is defined standard deviation? Do you remember how you define standard deviation? Let's say we have a variable x. Okay, we have a variable x, and its mean value is x. Okay, for example, in this case of throwing a dice, okay, if we do this calculation, we'll get some average value x, right? Then how can we calculate the standard deviation? Okay, we will continue in next class. Okay, I want to give you some. I want to revise some of this very basic concept of standard deviation and distribution function. Then we'll study this molecular distribution of molecular velocities, Maxwell-Boltzmann distribution and Fermi-Dirac distribution. Okay. Yes, sum of all the probabilities will always be 1, because the value should be between 0 and 1. If you have probability more than 1, that is unphysical. Okay, any question? We'll discuss, we'll continue this probability and then distribution function on Friday again.
सर थर्मल फिजिक्स के लिए कौन सा बुक रेफर करें?
Okay, thermal physics. Okay, thermal physics, there is one book by Weiser, Modern Physics. Weiser, Modern Physics, and there is also one book by Blundell. This
So
is
your screen is not visible.
okay. We'll discuss tomorrow. I'll give you the books tomorrow. Okay, you remind me once. This will be Weiser and this will be Blundell. You remind me tomorrow. I'll give you the list of books. Okay. Any other question? Okay, well, we'll start tomorrow. Tomorrow we have tutorial, and then Friday we'll continue again. Okay. Let's stop it here, and then we'll meet again tomorrow. Bye bye.